a word, when you go into a fabrication shop, it's a good idea to keep your hands at your side. And don't reach out and grab things. If you're walking through the lab and you see a piece of metal there and you grab it, well, somebody might have just been grinding on it or cut it and it might be hot, or you might have some burrs on it. You need to be a little careful. Okay? Not that it's that dangerous, but we're unfamiliar with that workspace, and you want to be a little careful what you're doing, what you're touching. Those metal, some of those machines you're going to see, they're pretty unforgiving if you get in the wrong spot. And I'm sure Cody will kind of be keeping you under tight rein, but just a word of advice. Test review. So tomorrow, we're going to start a little earlier. We need to start it at 8:15 to meet the schedule for the day. Any other questions on tomorrow? By the way, before we jump into the test review?
Questions about
What's that?
tomorrow?
Yes. No sandals, right? All pants, wear pants, that kind of stuff. He'll provide PPE. You don't really need gloves, right? John, you got a recommendation? What do they need to be in that lab and be okay?
They just need closed-toed shoes and pants, because if they want to weld, I'm sure that they'll have welding leathers to put over, so it doesn't matter what type of shirt you wear. Other than that, it should be fine.
Okay.
Does it cover your arms too?
Yeah, it's like, it's a big leather jacket.
Oh.
All right, so the test tomorrow. We'll start at 8:15. I'll allow you an hour. You will not really have to draw anything, so it's pretty much all academic. We'll leave the drawings for handling that. It will cover 2 chapters, chapter 22 and chapter 25. Only cover the stuff that we talked about, because there's more in those, right? I think we did all of 25, but 22 we just focused on gears. There'll be multiple formats on there on the test, so you know what to expect. There's going to be picking or matching. There's going to be multiple choice. There's going to be where you'll have some diagrams and have to know what the information says on it. Might be a good way to put that. Remember how, like, when I do a thread note and I'd say, have a bunch of lines, say what's the series, what's the form, what's this? It'll kind of be like that when I do weld notes. I'm going to do something a little different on this one to test a little bit of knowledge. I am going to do some plus minus mathematics. As you remember with the gear, it's fairly technical. We need to get a lot of data together before we go it. And so I'm going to use some math, and it won't be hard math. It'll be plus minus, multiply, divide type stuff, just to see if you know what or where we got some numbers. So expect 4 to 5 questions like that. There is a bonus. I break the test into 2 parts. In essence, one part is welding, one part is gears. As a reminder, so you don't have to go back through all the old videos, I'd like to run through the chapters real quick and talk about, or just re-talk about the pertinent areas. Are there any questions before we move on? Okay, let's start with 22. Okay, we talked about the classification of gears. Remember, they're classified two ways. Does anybody know the two ways?
One is by function.
No. No, it's not. We're talking about classification, so when we're in a certain situation, which gears do we look at? Remember, we've got
Shape
first,
and tooth.
okay, the shape of the tooth is one of the classifications. Because the shape of the tooth is going to drive really the condition. Do we need lots of torque on it? Do we need lots of power? Is it gonna run fast with not much torque on it? What's the classification of the operation of the gear? Okay, so we did one by tooth profile. There's another way to classify gears also.
Position.
What's that?
Position.
It is position, we call it shafting. Remember we talked about if I got parallel shafts or intersecting shafts, shafts at right angles. In that same classification, we also want to know the operation or how the gears are going to work together, because we do it, we're transferring power, right? But what else can we do with it? We can change the speed. We can change the direction. The shafts will change the direction. How do we change the speed?
Move it from a smaller gear to a larger gear. No.
No, you're right. From the pinion, which is the smaller, to the gear, which is larger. If they're the same size, you're not changing the speed. But if they're different sizes, you are changing the speed.
Change
So
the
we call
ratio.
that a gear ratio. That's how you calculated that. Remember, when you're calculating gear ratio, you can calculate it three ways, because these three terms are fairly, well, not fairly about it, they are symmetrical. And that is, you can compare diameter to diameter. You can compare number of teeth to number of teeth. And you can compare RPM to RPM. All of those will give you the gear ratio. Do you remember the equation?
RPM, opinion.
Our gear ratio is equal to, remember I wrote this one on the board?
I can't remember which one goes on.
This was for the number of teeth. N stands for the number of teeth. The subscript G stands for
Gear?
gear.
There was something I didn't really understand, because it seems like in general, to get the gear ratio, it's always the gear over the pinion.
It is.
But you also said that you could, and the pinion is where the power's coming from.
Well, they don't distinguish between that. I kind of talked about, because this gives you a positive number if you always consider the pinion small and the gear big, right? It's always a 3-to-1 or a 2-to-1 or whatever. It's a positive number. There are people out there, and it's an older way, it's actually how I learned to calculate it, is that because you're kind of interested, you got power in it to a device, right? And you want to see how it's affecting things downstream. And so what you did was you figured the power was coming in, and then you just always divided by that, and then the out was here. And so if the power in is a big one, power out is a small one, you're slowing it down. So your gear ratio would be 1-to-3 or 1-to-2 instead of 3-to-1. And you would just know by that and say, oh, I'm slowing it down or speeding it up. But they've changed that. Now they've simplified it. They just said you're doing this.
It just seemed like, since there's two different ways to figure it, the old way and the new way, that there would be confusion.
Yeah, and I probably just confused the issue by bringing it up. But I'm sure there's firms out there that still do that. And I'm sure there's machinists out there that come in and say, hey, make your ratio 1-to-3. Well, I'm slowing it down, because it's a third, right, coming out, as opposed to 3 to 1. It's just kind of a little vernacular thing. Don't get too confused on it. Gear ratio, you can do number of teeth, you can do RPM, you can do diameter, always do, put the small one here, large one there, okay? And you're good.
So the book had the gear ratio and the pinion ratio. You would be asked the pinion, because that's just the opposite of what you're talking about, right?
That's basically what I'm talking about.
Yeah, that's what you're talking about.
Yeah.
Do they still call it, would you say what's the gear ratio, what's the pinion ratio?
Mhm.
Okay, so you'd still,
Yeah.
the ballot, okay.
Have we kind of beat that one to death? Okay. Remember this picture? I think I used that one in the handout as opposed to this. Know the definitions of this stuff. You kind of know the ones that are related too. Okay, look for relations between them. And as an example, are the addendum and dedendum kind of related?
Yes.
They certainly are, because both of those two will describe the entire depth of the tooth, right? Working depth and clearance. They're kind of related to each other, aren't they? Or working depth is a different distance that the mating tooth comes in. Clearance is the distance that is unused. So again, you're describing whole depth. One thing you do want to be careful on these, because this, I'm going to use a lot of this as math and picking. When you look at the center line and the two phantoms right next to it, okay, we call that the addendum circle, dedendum circle, and pitch diameter. You're dealing with diameters on those. Okay, so if I say something like, hey, this is your pitch diameter, or here's your addendum diameter, here's your pitch diameter, what is the dedendum diameter? Don't forget, you've got diameters, so you might have to divide by 2. If I say, what's the dedendum? You could calculate that. But let me kind of give you an example. Just so you know, on this, before I get into this, you should know all of these terms or be able to recognize them. Now, we focused on about 8 or 9 of them, okay, but I think they're all pretty valid. Expect little pictures of this where you have to define what the dimension is asking for. Now, an example also might be, this is where I'm going to use some math too, to really kind of figure out if you know what this stuff is. And let's say I give you something like your pitch diameter is equal to 4.0. Your addendum diameter is equal to 4. Let's see. Kind of making these numbers up here. 4.2. Can you find the addendum? Go ahead, I'll give you a couple minutes. Give you a couple minutes.
Another question.
Yes,
It's not on that. It's on the gear ratio thing.
yes.
So you said we can use the number of teeth and the diameter of the RPM.
Mhm.
And you said the big number goes at the top, right?
Yes.
So. would
Well,
it be like-
not really with RPM. You put the gear RPM up there.
Okay.
Okay.
Yeah, because that was my question. Because like, what for the gear RPM, like, wouldn't it give you like the inverse of the
It
ratio?
would.
Because it's like backwards.
Yeah. Yes, it would.
So would you write it like the backwards way with RPM, or would you just know it's addendums?
No, you would write it the backwards way.
Is the addendum diameter the same as the addendum circle?
Yes.
So you lost it from page 50.
You get 0.25? Does anybody else get something else?
Oh, I got 0.25.
You got a 0.25? How many people got 0.25? Okay. One would get,
Still putting it
Missy?
Yeah, I don't know.
Okay. Well, what's the pitch diameter?
4.
This guy right here, right? What's the addendum? The outside of this, right there, the panel line. Okay. But what's the addendum?
in.
Now, it is the linear distance between the pitch and the diameter, right? The addendum is shown, where is it? Right here. So it's the distance from the pitch diameter to the addendum. So the answer here is 4.25 minus 4 divided by 2.
So it's 0.1.
It's an eighth. Right? These are diameters. So therefore, the distance between them, you've got a top and a bottom there. Let me draw you the whole circle. So I have phantom line. Perfect circle. Okay. Pitch diameter. Addendum diameter. You're looking for that distance, aren't you, with the addendum?
Oh, so it's half that, 125. I guess
Yeah.
it's half it is. Okay.
So you got to divide by 2.
It's diameter and radius.
Can you do this one? My hole depth is 0.6234. When I say hole depth, what am I talking about?
That was gonna be my question, because I didn't know when you use that.
Oh,
I
that.
don't know, I don't understand.
Hole depth is the entire depth of the tube.
So whole depth also
Under the
equals
two.
A plus B.
Yep, it's addendum plus dedendum, right? That's the whole depth.
Okay.
So here's your clearance. Can you calculate working depth? Working depth is the distance the mating tube comes in. While you're working this is in essence the same thing you had on your handout where you filled out that sheet, right? You had to go and figure all that stuff out. That's exactly what we're
Will
doing.
we have these formulas for this part of the test?
No, no, you won't. I'm gonna keep it fairly simple like these, the ones you should know. Okay. Am I gonna ask you the chordal addendum? No, I'm not. Okay, the ones that are pertinent to us. Anybody got an answer yet?
0.6078.
Looks right. Got that, you backed it up?
I got it.
Juan, did you get it?
I got 0.639.
0.639? Okay. You added this then, right?
Yeah.
So if I have a tooth, what's that dimension right there? Whole depth, right? The whole tooth. Now I've got another tooth. It does something like this. I don't know if I can draw this upside down. Okay. The distance from there is what? That one, right? The distance here is what? So to find the working depth, I would take the whole depth, subtract off the clearance. Okay, so I'm gonna take that whole distance, subtract that guy out, I'm left with that. So subtract that, 1. Just a word on calculators, just so you know, this is a test. You cannot use calculators on your phone. Okay, so make sure you bring a calculator. Because you can't use your phone, right? So come prepared for that. Yes, Cheryl, you got a question?
So you have a gear pitch diameter and a worm pitch diameter, and that refers, it's obvious there. And then you have the circular axial pitch and the gear diametral pitch. And I just haven't gotten them straight in my mind yet, the distinction. Because it seems like the circular pitch or axial pitch, they're doing it up here on the worm, which isn't really circular.
The axial pitch for the worm, what we're really talking about there is lead, right? Remember the lead, distance traveled in one 360-degree turn, but it's been converted to a linear unit versus,
Oh, I see, worm. So as far as the pitch goes, the pitch should be equal to the diametral pitch.
no. Diametral pitch is a ratio that we use with Wellman's odontograph to calculate tooth profile. It really doesn't have a lot to do with the tooth, it has to do with our approximation of the tooth profile.
So in addition to those that I just rattled off, then there's still just your standard pitch.
That's correct. That's the distance from one tooth to the distance to the next.
And that should be the same in the worm and the gear.
Say that again, please.
The worm pitch, the pitch should be the same for the worm and the gear. Because they have to go together.
No. You're missing one component there. What is the pitch diameter? Let's go back to that. What's pitch diameter? Because we got to go back a little bit, Cheryl, for me to answer this question.
Okay.
We gotta make sure we really understand the root component. What is the pitch diameter? It's the most important diameter with a gear tooth for power transfer. What does the pitch diameter tell us?
The center of the tooth.
No, it's not center. Not
Center of
center.
the gear.
What?
Center of the gear.
No, no.
Is it where the most power in the tooth is?
It is. It's where the mating tooth comes in and they're tangent to each other. So it's where all the power gets distributed between the two teeth. Because picture those things as they roll together, when you got another one in here and it comes in. Okay, remember, it's coming in at an angle, right? And then it rotates through. That's where it's contacted, right there. And as the two teeth come in on different angles, it's gonna hit and then just roll right along that point. And that's where all the power transfers through. So that's really what you're doing. That's what you want. It's where that mating happens. That's the pitch diameter. So it's the most important one. It's not right in the center of the tooth. It's generally a little bit higher than center. It's not geometrically this, but think of it this way. You know you got your working depth that the two teeth are interacting? It's really kind of in the center of that. Okay. So Sean, you mentioned the center of the tooth. No, not really. It's the center of this working area. Okay. That's kind of what it is. And that's how we're transporting the power from one device to the other. Okay. Now, the two pitches do not have to be equal because these are two separate devices. They're two different gears. Remember, you can match a spur gear up with a rack gear, a worm gear, another spur, whatever. But the thing you do know is that the two mating teeth will meet on that line. But they don't have to be the same. I mean, as an example, back on your desk, we had all those gears. Are they still there?
They're right there.
Moved them over here?
Yeah.
So here's what you're, in essence, drawing. These two, right? Spur and a worm. Okay. They mesh up like such. If you look at this, the teeth aren't even close to the same. This one's an